Hello students, continuing with our topic of multi-degree of freedom system and finding the natural frequencies of multi-degree of freedom system. We have seen many methods of finding the natural frequencies of multi-degree freedom system, such as matrix method, then influence coefficient method. In influence coefficient method, we have seen stiffness influence coefficient method, flexibility influence coefficient method. Then we have seen the Holzer method for spring mass system, for rotor system. Then we have seen the Stodula method, Rayleigh's method. Now continuing with our topic, today we'll see the Dunkerley method. So Dunkerley method is basically used for finding the natural frequency of multi-degree of freedom system and finding the critical speed of a rotor system. Basically, Dunkerley method is developed by the US mathematician Mr. Dunkerley for the rotor system. So the basic this Dunkerley method is basically derived, or it is developed for the rotor system. Okay, so first we'll see the characteristics of the Dunkerley method. The first characteristics is it is used for the rotor system. You cannot apply this method to a spring mass system. It is basically developed for the rotor system only. Then second is it is an approximate method. We know that the Holzer method, Stodula method, these are approximate methods because a lot of assumptions are involved. Same goes with the Dunkerley method as well. It also involves some assumptions, and because of those assumptions, this method makes it an approximate method. Then the third point is each rotor is modeled as a point load on a simply supported shaft. As I said, this method is applicable to the rotor system. That means a number of rotors are installed on a shaft. The shaft is supposed to be or assumed to be a simply supported shaft, and all these rotors are modeled as a point load on the shaft. Okay, so simply supported beam with point load acting at various points. This is how you can model the rotor system in this Dunkerley method. Okay. The examples of a shaft mounted with number of rotors, you can find it in multi-stage turbines, where turbine rotors are installed on a shaft. Then another example of such multi-rotor system is multi-stage pump. You can have a number of impellers on the shaft. So these are some of the examples of multi-rotor system. And the number of rotors on the shaft determines the number of degrees of freedom of that particular system. If there are 3 number of rotors, then the degrees of freedom is 3. If there are 4 number of rotors on the shaft, then the degrees of freedom is 4. And that means number of natural frequencies will be there in the system. If there are 3 rotors, then there will be 3 natural frequencies. If there are 4 rotors, then there will be 4 natural frequencies. Now number of rotors will decide the degrees of freedom. As I said, the number of rotors will decide the degrees of freedom. So 3 rotors, 3 degrees of freedom, like that. Now this particular Dunkerley method is also used to find out the critical speed of the rotor system. Now what do you mean by critical speed? Now before seeing the critical speed, I will take you to the spring mass system. Now consider this is a spring mass system. Consider this is a spring mass system, and this spring mass is acted upon by an external force F0 sine omega t. And when this external mass is acted upon by an external force F0 sine omega t, where omega is the excitation frequency, and when this excitation frequency get matched with the natural frequency of this spring mass system, this mass will vibrate exponentially, or this mass will vibrate very severely. Why? Because when the excitation frequency becomes equal to the natural frequency of the system, there will be resonance, and because of the resonance this mass will vibrate quite high, and this resonance needs to be avoided. Okay. So same goes with the rotor system. Instead of using a resonance phenomena here, critical speed is used. When this is a rotor, and on this this is a shaft, and on this rotor there are three rotors installed on the shaft, and when the shaft when the rotor is installed on the shaft, then the shaft will have some static deflection, and when the in dynamic condition, when the shaft start rotating, then the deflection also goes on increasing. So if you increase the speed, then the deflection will increase, and there will reach a point, or the shaft will reach to a critical speed where the deflection because of this rotor will be maximum. So the deflection because of the rotor will be maximum. That speed of the shaft is called critical speed. Critical speed. And this critical speed is nothing but the natural frequency of this rotor system. When the shaft speed becomes equal to the natural frequency of this rotor system, then the deflection occurs in this rotor system will be maximum. If you further increase the shaft, then the deflection gets reduced. So at critical speed, the deflection of the shaft will be high. So this critical speed phenomena can be related with the resonance phenomena in the spring mass system. Then by using Dunkerley method, you can find out the natural frequency of the rotor system. For example, there are three rotors, rotor 1, rotor 2 and rotor 3, and if you model each rotor as a single point load and find out the natural frequency of only one rotor on a shaft, and Fn2 is the natural frequency of the rotor system when there is only rotor number 2 on the shaft, and Fn3 is the natural frequency of the rotor system when there is only third rotor on the shaft. And then by using this formula, 1 upon Fn square is equal to 1 upon Fn1 square plus 1 upon Fn2 square plus 1 upon Fn3 square, you can find out the natural frequency of this combined rotor system. So this is the basics of Dunkerley method. Now we'll see one problem, and there will apply the Dunkerley method and find out the natural frequency of the rotor system. Now here you can see that there is a shaft, and the diameter of the shaft is given 60 mm. There are 4 rotors installed at equal distance. All the rotors are placed at equal distance. The total length of the shaft is 5 meters. Each rotor weighs 50 kg. So rotor at B weighs 50 kg, rotor at C weighs 50 kg, and like that all the 4 rotors weighs 50 kg. Then the value of Young's modulus is given 200 GPa, and we need to find out the natural frequency and critical speed of the shaft. So according to the Dunkerley method, we will consider one rotor at a time. First we'll consider the first rotor, which is at B. So this is the rotor is modeled as point load. The shaft is simply supported. The distance of this point B from the F end is 4 meter. The distance of point B from end A is 1 meter. And according to the design data book, you will find the deflection formula for simply supported beam with a point load acting as WB into X upon 6 LEI into L square minus X minus B. So here W stands for the weight acting as a point load. So here the W is nothing but 50 into 9.81 Newton. So W is 50 into 9.81 Newton. This is the point load acting at point B. Then this B is nothing but the distance of point B from F end. So this is 4 meter is the B. X is the distance of B from the end A. So this 1 meter is X. Then this L stands for the complete length of the shaft. E stands for the Young's modulus. The Young's modulus is given in GPa. So we'll convert into Newton mm. So we'll put all these values in Newton mm only. So convert this 200 GPa into Newton per mm square as 200 into 10 to the power 3 Newton per mm square. So we know that megapascal is nothing but Newton per mm square. So we'll convert the gigapascal into megapascal as 200 into 10 to the power 3 Newton per mm square. Then I is the moment of inertia, which is given by pi by 64 d to the power 4. The diameter of the shaft is given 60. Then we'll put all these values in mm and Newton, and we'll get the deflection because of the rotor at B as 4.12 mm. Then we find out the natural frequency in radian per second by using the formula under root g by delta or g by the deflection. So here we'll put the values g as 9.81 meter per second square, and the deflection comes out to be 4.12 into 10 to the power minus 3. Here we'll put the values in meter, and we obtain the omega NB as 48.79 radian per second. Similarly, we can find out the natural frequency in hertz as omega NB upon 2 pi, and it comes out to be 7.7 hertz. In the same fashion, we find out the natural frequency because of the rotor C only, and it comes out to be 5.13 hertz. Because of the rotor D only, it comes out to be 5.13 hertz. Then because of the rotor at E only, and it comes out to be 7.7 hertz. Then according to the Dunkerley formula, the natural frequency in hertz can be found out by using 1 upon Fn square is equal to 1 upon Fn B square plus 1 upon Fn C square plus 1 upon Fn D square plus 1 upon Fn E square. And when you put the formula, so this is the natural frequency of the rotor in hertz. So here you can find out the critical speed. So first you convert it into omega n as 2 pi Fn. So 2 into 2 pi into 3.01. So this will give the answer in radian per second. And to find out the critical speed of the shaft, we know that omega n is equal to 2 pi n by 60. Now we know the omega n, and you can easily find out the value of n. N is nothing but the RPM of the shaft. So you will easily find out the critical speed of the shaft in revolution per minute. Okay, so this is how you can find out the frequency and critical speed of the shaft. Now here we neglected, in this problem we neglect the weight of the shaft. Okay, so here we neglect the weight of the shaft. So I hope you understand the Dunkerley method and how Dunkerley method can be used for finding the natural frequency and the critical speed of the shaft. So thank you very much.